So we want to prove this theorem. A polynomial f over field f with characteristic of field f 0. This is solvable in radicals if and only if its Galois group is solvable. So first we prove in this direction, that is solvable implies solvable in radicals. So recall what solvable in radicals means, that you have this tower of field extensions or extension by radicals, where you construct this fi plus 1 by adjoining alpha I to fi. Alpha I to the power of ri lies in fi, so this is nothing but fi. You join alpha I to it, some power of alpha I lies in here, and this power is linked to this polynomial because alpha I is just root of this polynomial. So that's why you have these radical extensions. These are constructed using these polynomials. And finally this k contains the splitting field of f. So we have to show something like this exists. So again recall that cyclic extensions are of the form f alpha, alpha to the power of n lies in f, where f contains the primitive root of unity. So this is going to be our lifesaver. So because you have these cyclic extensions here, and that is precisely what is going to get transported. And we had that Galois group of f over a smaller field f contains the Galois group of f over some f prime. So f prime lies over f, and then you have the opposite direction for the Galois groups. So this we proved in the previous lecture. So let f over f have a solvable Galois group. So we have a solvable Galois group. So we are starting from a solvable Galois group. And first thing, we construct this extension f prime over f. So this f prime you construct over f by adjoining zeta, where zeta is a primitive root of unity for some very large n. So this n you can take as say degree of our polynomial f and then factorial. Why are we joining this zeta to it? We are joining the zeta to it because we want to use this result. We want to use the result of cyclic extensions of this form. So this form is linked here, but here f contains primitive root of unity. So you get cyclic extensions only if f contains the primitive root of unity, and that is precisely why we want to construct this f prime. So from solvability we have this sequence of subgroups like this. So normal sub g1 is a normal subgroup of g0, gi plus 1 is a normal subgroup of gi, then you have gj is a normal subgroup of gj minus 1, and you end at identity. So, and this portion is cyclic. gi over gi plus 1 is cyclic. So notice that this cyclicity of Galois group is precisely what is the cyclic extension here. So we had discussed cyclic extensions of Galois groups or cyclic Galois groups in detail. So we are just recalling facts from there. So this is cyclic, and say k is the splitting field for f over f prime, then you can use this Galois correspondence to construct these fields. So corresponding to identity, you have your splitting field. Corresponding to gj, you have your fixed field. Corresponding to gj is k gj. Corresponding to g1, you have this field. Corresponding to g0, you have this field, which contains f prime, which we are saying f adjoined with zeta. So now we are just using Galois correspondence. This is given to us, and this is our correspondence from the fundamental theorem. Now we just put this kgi as our fi. So this is increasing, so you see that fi plus 1 is cyclic over fi. So the cyclicity come from here. gi over gi plus 1 is cyclic, and this gives us this cyclic. So you get this form fi plus 1 is to fi you attach alpha I, where alpha I to the power of degree of extension, that is this degree of extension is nothing but fi plus 1 over fi, this degree of extension. So this alpha I raised to this degree of extension, this lies in fi, and this implies that we have been able to do this part. So this is done. So alpha I Ri lies in Fi. So you have solvability by radicals. So again, notice that this once you have the cyclic here, so this cyclicity comes from the cyclicity here. So this is the one, the terminology here carries over here. So this is cyclic precisely if your corresponding Galois groups are cyclic. So now from here to going to here, we have used this form, cyclic extensions. You have cyclic extensions, so they are of this form, f alpha, alpha to the power of n. So this is the one which we are using here. So yeah, so we are using cyclic extensions, and precisely because we wanted to use this result, we wanted to come here, that we had to have f contains a primitive root of unity. Otherwise we could not have been able to use result right here. So precisely that's why we adjoined zeta to it.